Concrete reinforced with steel is the foundation of our modern society. Reinforcement within concrete creates a composite material, with concrete providing strength against compressive stress, while the reinforcement provides strength against tensile stress. But while steel reinforcement solves one of concrete's greatest limitations, it creates an entirely new problem. Corrosion of embedded steel rebar is the most common form of concrete deterioration. So what are we doing about it? Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're testing out some innovations in concrete reinforcement. Although unprotected steel is naturally prone to corrosion or rusting, when it gets embedded into concrete, certain factors work to protect it. First is the obvious protection of simply being shielded from the outside environment by a relatively impermeable and durable material. Water and contaminants usually can't make their way through the concrete to the steel. The second form of protection is the alkaline environment. The high pH of normal concrete creates a thin oxide layer on the steel that provides protection from corrosion. But in some cases, this protection isn't enough. One of the main sources of corrosion to rebar is salt. Whether through exposure to salt water near a marine environment or application of de-icing salts to make roadways safer during the winter, these chloride ions can make their way through the concrete, corroding the steel reinforcement. And when steel corrodes, it creates iron oxide that expands inside the concrete. This expansion generates stress, sometimes called oxide jacking, and is one of the primary causes of concrete deterioration. So how do we prevent these chloride ions and other contaminants from reaching the steel and causing corrosion? The first line of defense is cover. Cover is the minimum distance between the outside surface of the concrete and the reinforcing steel. And depending on exposure and application, certain codes specify different amounts of concrete cover, generally between 25 and 75 millimeters or 1 to 3 inches. Cover is one of the reasons good concrete work takes so much effort before the concrete ever shows up on the job site. Installing strong formwork and lots of wire tying all the reinforcement together help make absolutely sure that, through all the jostling and walking over and general chaos that comes when it's time to actually place concrete, the rebar stays where it was designed to be embedded within the final product. Neglecting these steps can cause rebar to sink to the bottom of a slab or come too close to an outside surface before the concrete cures, eventually leading to premature corrosion of the reinforcement due to lack of cover. But even with adequate cover, any crack in the concrete could allow water and contaminants into direct contact with the reinforcement, and it won't surprise you to learn that cracks in concrete aren't all that rare. Most concrete shrinks as it cures, which can lead to cracks. Changes in temperature also cause expansion and contraction, which can lead to cracking. Concrete can also crack under normal, expected loading conditions due to the way that steel takes up stresses within the material. One way to solve this issue is by pre-stressing the rebar, a topic I discussed briefly in a previous video and something I'd like to dive deeper into in the future. But today I want to show another option for reducing these cracks. Fiber-reinforced concrete is pretty much exactly what you'd expect it to be. It's not a new idea by any means, but our understanding and use of different kinds of fibers within a concrete mix continues to grow. Adding glass, steel, or synthetic fibers to concrete can provide a lot of benefits, but one of the most important is crack control. I constructed 3 nearly identical reinforced concrete beams to show how this works, and I let them cure for about a week. The first one only has steel rebar as reinforcement. I'm using a hydraulic press to test out the strength of each beam and see how it performs prior to failure. And I'm using tons as a measurement of force on these beams just because that's what the gauge says, but the units are completely arbitrary to the demo. If you prefer SI, just pretend these are metric tons. As I increase the load on the beam, you see cracks starting at only around 3 tons. These cracks form because steel stretches a little bit as it takes up tensile stress in the concrete. The beam is holding the load just fine and isn't even close to failure, but concrete can't stretch along with the steel, so it has to crack. You can imagine how these cracks could let water and air into contact with the reinforcement and eventually deteriorate the concrete. Those cracks are the important part of this demo, but I went ahead and increased the load until the beam failed, because hey, that's what hydraulic presses are good for, right? For these next two beams, I included fibers in the concrete mix. One beam has steel fibers mixed in, and the other glass fibers. The steel rebar and fibers team up to resist tensile stresses in the beams. The rebar provides a large-scale reinforcement to resist tension across the entire structural member, and the fibers provide small-scale reinforcement to resist localized tension that causes cracking. When I load these beams up to 3 tons, you can't see a single crack. In fact, for both of these beams, I didn't see any cracks form until almost double that, and even then the cracks were much smaller. Both beams failed at about the same load as the first one, which I expected. Like I mentioned, the fibers don't really add much overall strength to the beam, but you can easily see that they could go a long way in preventing corrosion of steel rebar. You may be wondering, why are we even using steel for reinforcement at all? Steel is relatively inexpensive, well-tested, and strong, but lots of other materials have excellent mechanical properties and don't face this issue of corrosion. For corrosive environments, we sometimes use epoxy-coated rebar or even stainless steel. But there are some emerging alternatives to reinforcement like fiber-reinforced polymers or FRP bars. This is reinforcement made of basalt, remelted volcanic rock forced through tiny nozzles to create fibers that are extremely strong. Options like this often cost more than steel rebar, in some cases a lot more. But the major impediment to the use of these newer, more innovative types of reinforcement isn't just the cost. It's easy to see that those additional costs might be offset by the increased lifespan of the concrete. Another inhibition comes simply from lack of widespread use. Innovation happens slowly in civil engineering because the consequences of failure are so high. Gaining confidence in a design has as much to do with engineering theory as it does to simply seeing how well similar designs have performed in the past. But many engineering disasters have come not just at the expense of bad design, but actually bad maintenance. So long-term durability can be just as important to public safety as other design criteria. We'll certainly be seeing more innovative ways to reinforce concrete in the future, including some of the things I mentioned in this video. Thank you for watching, and let me know what you think.